Welcome everyone to another amazing FPGA live stream. A little bit intro melody because pulse width modulated direct stream digital audio, because why not? Here played from the FPGA. And as you probably can see, so this is a capture directly from the HDMI output, and this is the kind of final version for now, also anyway, of our FPGA Verilog video soft core of generating HDMI signal. And I kind of completed it, wanted to present you as a final update, which is, as you can see here, not only text mode. So this is like earlier we first had to get started and get into all the details and get experience and learn a whole bunch of lots of details. And earlier the stuff was off by 1, off by 2, off by 3, memory load delay, 8-bit versus 16-bit bus, and all these fun details. And in the meantime, you see it is pixel perfect now, which would be this view here. So now it's pixel perfect, as you probably can see. So this is an 640 by 480 16-bit color palette color. Initially, I wanted to have this completely VGA compatible, although initially I somehow didn't read the fine print here precisely enough of the icebreaker. And the issue is we are a little bit memory limited. So we use all of this 1 Mbit 128K single port memory for the RISC-V core, which we also have running on there, the Pico RV32. But this dual port memory, I somehow overlooked that these are K bits. So initially I was targeting for 320 by 240, 265 colors of VGA fame. Unfortunately, we don't really have that memory unless we would sacrifice quite of the system memory of the RISC-V. So we could halve this, but I rather have 128K for the RISC-V software and somehow live with a smaller frame buffer. We could theoretically make this 32K, but something about anyway. Maybe eventually we work with larger FPGAs sooner or later. Anyway, another really nifty thing that I implemented here, which also I need to get used to this camera views again, is also graphic mode. So on the very first videos, previous videos, if you want to get into all those details, I also had pixel data streaming out of there, even with shades of gray, maybe was it 4-bit gray or something. But again, we don't have that much memory. So I opted for now with 1-bit black and white, or actually 1-bit the first and the last color palette. So you could change this, you could make this black and green or blue and yellow or whatever you wanted to make that. And to have at least a somewhat decent resolution of 320 by 240, we can toggle this here in this test firmware, which are also too many. Would this be? No, this is too many scenes where it's even. Anyway, whatever. Here with this UART still connected, so we have here some commands. So that would be J for graphic mode, and as you can see, we get there some quite distorted picture. That is because we switched to graphic mode. So I even not only have implemented graphic and text mode, but we can also switch dynamically, which also probably have this camera view. So we can switch dynamically, and I have another test. So this is with test data. This is why there's quite a bit of Lena test picture to be seen. But of course, I have here also capital G for loading the whole picture. The other picture was FPGA memory initialized with this test picture just for the testing fun of it. And now we have the RISC-V core here from this UART, giving it. So not only can we toggle this here with those commands for playing audio and doing graphic stuff for testing purposes, but also either, for example, so this would be back to text mode. Of course, now it's a little bit garbled, because totally expected, because we switch back to text mode and we do not clear the memory for testing purposes and fun. So what you see is just those pixels of this Lena pixel in the frame buffer, just defining some random text. And because we have a character set in video memory, as you see now, we have some text garbled. That is only because our frame buffer data is overwriting the character set. So as you see, some characters up to, you see their mode and stuff, benchmark is still okay. That is because we need 9 point something K, so we're overwriting the first 40 or something characters there when we toggle. We can also, so with G here for the testing purposes, you see when we switch back here from text, so here, dynamic mode switching for, because we are kind of sort of perfectionists anyway. So yeah, dynamic mode switching, also, yeah, that is certainly pretty fast. And yeah, for actually, so also this pattern there is with the non-frame buffer filled. So, sorry, did I say it was raining here in Berlin, right? So this signs there are, by the way, just I fill for testing purposes to debug this. I fill the very first 16-bit of graphic here with this test stripe pattern. So this is actually, there you see the locations. They are 320 bytes divided by 16 or so, multiplied by 2, because character set and text attribute apart. This is just the distance of the frame buffer scan lines there. And again, of course, with capital G, our freshly from the RISC-V, from the flash written here, this picture. Of course, now we could write a game like Pong and Tetris and Pac-Man. Maybe some, also, yeah, of course, we can totally improve this theoretically if we have some logic cells left. By the way, that this is filling there, the pattern you see there is some pattern overwritten in there. This is, by the way, kind of by, well, design. It's a side effect of, you see we have here this command prompt printed, and that is just printing there as it if would be text mode. So you see this is if you write into frame buffer for text characters and then you are not in text mode but in graphic mode, and then of course you get just this bit pattern of this greater sign here for the command prompt imprinted there. So that is totally working by design. If we toggle back, then as you see there's a menu. Anyway, so totally amazing stuff. As far as I know, there is no off-by whatsoever stuff going on. And if you're interested, I can give you a complete run. Welcome everyone there. By the way, so if you're interested in the code, also we are running out of logic elements. So I've right now, I already had to optimize this a little bit. So this is the video core stuff. I hope that is somewhat, it's pretty large for me, so it probably should be somewhat okay for you. If you are interested, I could go here over all the code. It's also already on GitHub already. Yeah, I actually employed quite some tricks to get that far. And again, so the only thing, so we have amazing sound, well, 3 voice and random noise, kind of sort of amazing noise. And this video core, and I have like right now I have only 10 or so logic cells left. Most likely I have to strip down some features or optimize this a little bit to have keyboard and mouse, the last missing point. That will be a little bit challenging, but maybe more to this later. I hope I don't need to strip so much out. Certainly I don't want to strip something out, but yeah, 5,800 something, probably it's written here, 5,280 logic cells, yeah. There is also, so if you want to see, we employed here quite some fancy Verilog. So we define our module here for dual port memory, as we learned the hard way to actually make this behavior analysis, instantiate this SOTO logic cells that it's using dual port memory here. Also new since yesterday, I still have to further improve this. For example, theoretically, I have here already to do parameterize width, so data width. Right now it's hard coded for 16-bit. Theoretically, it would be nice to have here a parameter for width and size and not hard code this here. That would be that. It's totally easy thing. Maybe these are the things of like, yeah, now everything is working. We can also make it a little bit more pretty. Initialize here with some memory. I have here some parameter now for that. This is just that the FPGA comes up with a correct character set, loaded into character for exactly this pixels, not to be garbage. We can also actually reset this, as you see then. we are coming in. Actually, when we boot up like this random pattern is not random pattern. It is actually, if we quickly switch to graphic mode, this is actually preloading Lena with this initialization. So the bitstream, the FPGA bitstream has initialization for the Lena in graphic mode and the character sets in filling the frame buffer, VRAM and character set. So if we unplug this here quickly and do here screen this and quickly switch to graphic mode, then you see it was initialized with the Lena here from the FPGA bitstream, just that we already printed so much stuff there that it's partially obviously overwritten with the same video RAM on text versus graphic. And again, those dots there are completely fine. If we scroll here, this is not like some bug. It's just, as I said, this text pattern of the first line there of text pattern. Amazing stuff, completely perfect. So then here is a Vga module. It gets a clock, reset pixel clock to be generated, passed in. The PLL needs to generate this. Then some system bus. Select ready write byte selected there from the RISC-V CPU, some address, write data, read data. Then the outputs to the PMOD here for the FPGA pins, just like on other icebreaker examples. These are just the pins on the PMOD there. Then defining, mapping those pins to our video RGB stuff. Then instantiating here our some output buffer to repeat the pixel clock from the original example. So then memory mapped I/O bus interface, having some register for the read data to receive those read data. Actually, I wonder if we can we avoid this? Anyway, need to check. Then the video signal. We have here some vsync vertical horizontal sync data enable coming from the video timing, also previous video I had to, so not both examples I used were off by too much. I had to debug them to know, and for hours and afternoons. Mostly nearly completely rewrote this to have pixel precise control over X and Y position there. So this is coming out of the video timing, previous video. Then yeah, this is a video timing, so instantiating the video timing module of pixel clock, getting the inputs and outputting H-sync, data enable and X and Y pos. So this is the only input and it's outputting from one pixel clock. It's generating all the video timing signal. Then actually output test pattern, this comment is old. Output, can actually rename this to RGB output because it's not a test pattern anymore. So these are just our 4-bit RGB, horizontal, vertical, sync. Actually, I slightly wonder, do we really need this? Or maybe this wires coming. Anyway, some frame counter also. Yeah, actually, so theoretically we could do away with the frame counter. We could have some 16 or whatever logic elements to be saved here. I think we don't really need this anymore. This was from the example. This is some linear frame buffer address counter, mostly for the graphic mode. Theoretically, we could rewrite some parts, maybe even saving some logic elements or adding some features. For example, right now I only use this linear address counter for the graphic mode. Theoretically, we could use it for the text mode. For example, implementing hardware scrolling. Right now we use 128 byte lines. Very theoretically, we could change this, maybe even making this more fancy hardware scrolling and saving logic elements while at it. Also, this probably we don't really need. So theoretically, we could save another couple of 3 bits here. This is just from the original example. I don't really need this anymore for something, I think. Then, yeah, the VRAM interface. So we're instantiating here 2 dual port blocks. One for the VRAM of 8K size and one for the font character memory of 4K size. So in total, we're using 12K of the 15K. So theoretically, there's still some room for adding a couple of more bits for attributes and sprites and whatnot if we would have just a few logic elements left. But first I need to squeeze keyboard and mouse in there. So probably we don't really have many logic elements left. This is just original VRAM initialization test stuff. I think we can probably actually even delete this. This is just, yeah, we can clean this up. This is just from early drafting. Then one bit for text versus graphic mode. As by my previous videos, just like now we dynamically set this. So if this register is changed, it switches the logic that we implemented, and nothing is for free or working by itself. So everything, so this is one hardware register bit that we toggle for switching here between those funny modes. And then yeah, pixel data. So this we cache for. This is our logic, our cache in terms of logic cells or flip-flops to cache our current pixel data, our text attribute and text row bits of 8 bits of forming the current text. For example, a T like 0, 1, 1, 1, 1, 1, 1, 0 or something of a T there. It's a beginning of a this kind of pattern there. Some neat tricks I learned. So I heavily combined sequential and combinatorial logic. So earlier I computed those masks in the pixel clock generation. However, I learned that it is much more efficient and faster, because if we, for example, with this blocking versus non-blocking assignments, if we have a non-blocking assignment, then of course this only updates at the end of the cycle. So for example, this here is combinatorial logic of always without flip-flops not having this buffered, and this logic is like always active, as in the 0 and 1 binary input, it's always receiving those. So as soon as those register bits toggle, the output is with a propagation delay of a couple of nanoseconds. So how long these logic elements need to switch. So this mask is used, as you see, for the masking the text character, and it is much more efficient to hardwire this. So this is a hardwired shift right directly from the output from this X position register, and so this is running always with like the full clock and instantly flipping those bits as soon as the bits change in the register. This is updating, of course, with the propagation delay of the logic elements, but rather instead of having this one clock cycle later. And this is also the magic here. So the big work was actually optimizing this to use as few clock cycles as possible, because as we learned the hardware with, initially we had 1, 2, 3 pixel delay. Learning here the hardware of course, with your clock, the output signal of pixels need to be like instantly available. So the whole point of this was to get rid of all the off by 1 and off by 2 and off by 3 stuff, was shadowing and hiding all the memory access delay and computation of those bit patterns, especially for this graphic mode, for this text mode. Because in graphic mode we stream out those bits rather instantly. However, in text mode we need, for each text cell, need to load the VRAM data, and then after receiving this, which in our design takes actually 2 clock cycles, because the memory is apparently not faster as we run this double data rate, and with the PLL driving the pixel clock at 26 megahertz, 2 times faster than our system clock. I learned the hard way, we need 2 clock cycles on the pixel clock to reliably load stuff from the memory. That was actually quite tricky. Then, also hardwired foreground color. Initially, in my previous videos, I assigned this with non-blocking statements that had a 1 clock delay of propagating this from the flip-flop that latched this in the positive edge of the pixel clock to the end of this clock cycle. And to have those data, learning this the hard way, optimizing the heck out of each clock delay here, having this hardwired combinatorial logic here means that this foreground color here are wires that we directly assign to the bits of this text attribute, VGA compatible. So the first 4 bits the foreground color, and then the next 3 bits background color, and then the blink attribute. So they are permanently hardwired to those register bits, and when those register flip-flops toggle and change for something, they instantly, like again with the propagation delay of the signal time there, but rather instantly change. Then a lot of registers, and I optimized them already as per previous video. Initially I had some 24 bits, but we only have 12-bit color output anyway, and anyway usually only run 16-bit colors anyway, of which we can only output, not 16-bit, 16 colors, of which we can only output 4 bits anyway, so I halved them all previous video already, so just to save like half of all the logic elements here. For why waste them if they are invisible anyway? Then quite some massive amounts of registers for the cursor pattern, which I, as you can see here, load with some default stuff. So this is 2 bits, just like usual hardware cursors of previous video, PS3 and all the other fun videos where we did hardware cursor, even on the Octane, if you're SJ Octane hardware cursor stuff on the Impact. Just how is this implemented in hardware, similar to this, as you see on the PS3 and SJ Octane and other fun stuff. This means that we can have an independent hardware cursor and do not need to waste CPU cycles and whatnot. So this is instantly blitted over the pixel data here at whatever locations it might be, which we can also change already. So there's our hardware cursor, and also, of course, this is mode independent, so at least it should be. Why is this not? Also, where is, by the way, my hardware cursor? Oh, yeah, right, it's just not the most visible it looks, I guess. Oh, yeah, there it is. Of course, it's working anyway. So yeah, hardware cursor. Also, fun fact, right now we do not have a blinking cursor, and I think I will not waste a single logic element for a blinking text cursor. However, we can nicely emulate this, maybe even in a fancier way with this hardware cursor. So we can misuse or reuse this 16 by, what do I even have here? 16 by 16, I think. Maybe I should comment this here for like 16 by 16, I think I made this. And this is 16 by 16 because for each pixel we have foreground, background color, and transparency and invert. So with this we can make a really super fancy blinking text cursor by just moving this hardware cursor to the location that we want this to blink, or so we can have underline or full block and inverting, so super nice. We can even theoretically, maybe we do this later or something, or tomorrow, we can have this even like a block cursor and the like underline, like inverting, like the top half, or not, more like the top 80% or something, inverting differently than the underline, or some fancy stuff there. Cursor position, the current cursor row, which probably we can actually optimize away. So probably we can probably directly address this here. I would say so most likely here probably a couple of more logic elements to save if we hardwire this similar to that here, and have here makes this a wire and maps this directly to assigning this to cursor X position, mapping this to this could potentially save a couple of 4 or 8 logic elements, logic cells if we are lucky. Similar to this, see here is the current cursor X and Y position. This is again combinatory logic of instantly updating this from the cursor X and Y position based on the currently drawn X and Y position there. So really nice stuff. This is a palette, so similar to the DAC, the digital analog converter output palette. We have here 2 cursor palettes and some register I needed to optimize the bus interface. So here's the pixel clock, so on always positive edge pixel clock. We update this H-sync, which by the way, we don't really need this anymore. I think this is only from the example code. I think probably not really used for anything. Now we only output this. So this are a couple of more logic elements to be saved. We don't really need a frame counter here, I would say. So although if we add features, for example, we could add an interrupt like vtrace, vertical retrace interrupt. So if we remove this and want the RISC-V receiving an interrupt, most likely we spend the same number or something of logic cells to implement the interrupt. Then yes, theoretically we can clean this up a little bit. This is still old test code. You see if one, this is just, yeah, we could certainly delete this now. Then if text mode, so this is a really tricky part. So as you heard in the previous videos and today a couple of times, we need to preload the VRAM, because when we get the pixel clock and we need to output a pixel, like say we output the first pixel 0.0, we need to have the data already loaded. I was thinking maybe implement this differently, like having some pixel pipeline and like compute at 0.0 compute, but in my opinion it probably would get way more complicated to like push the pixels like in some kind of delay through some kind of pixel pipeline delay stuff, like first in first out something. So I opted to rather fix the video timing to give us some negative number for front porch of the synchronization signal of front porch. I can also show you that here in also probably in VGA signal. Here I had this in previous videos, but this looks like whatever that. Although this is slightly, we usually had a nice, slightly different graph of signal timing. Probably there was this other. This is what we usually used. And so we start with negative. We changed this in another video because we figured all the details and everything got a little bit complicated. So my updated code outputs a negative position here. So this is 0.0. And with this allows us also to track when we are in sync signal or not. And this allows us really nicely to preload this. So we always output some pattern, whether it is displayed or not. This means we start at negative pixels as well. And this allows us to this code here. Earlier I had this here more open coded as in if equal minus, for example. Then I figured this with two complements logic, it just works if we load, so we do not need to specifically code this for negative something. We preload every, like we have 8 pixel clocks for 8 pixels of each text character cell, and we preload on each third, like exactly in the middle of the pixel, and there's a reason for that, coming to that in a moment. And so we preload this in the middle of each text cell at clock 3, and we start, so we assign the memory, the VRAM, video memory bus address to the position where we load from, like X and Y position. So like 0, 2, like with text attribute, it's 0, and 0 is text and 1 is the attribute. So 0, 2, 4. And so this is a VRAM address. And then as we learned the hard way, this is not coming out there instantly. So this is why this is 1 clock cycle delayed in our example, because we double data rate this. We actually need 2 clock cycles because we overclock this a little bit here. This is also the Yosys timing will not check this for us. The Yosys timing will tell us this design is good for 14 megahertz in this IS40. And although we run with 26, so we need to be a little bit careful. But this is also the point of many other examples. They usually synthesize with 12, 13, 14 megahertz, although they run at much higher, even as high as 1920 by 1080, but like not like validating the clock frequency for the pixel clock. It's like, yeah, we are lucky and maybe it works. I need to figure out another day if we can attribute this signal to for Yosys and ICE timing to validate this. However, right now this would fail. Earlier, before my design became so complex, this signal would validate to be good at 28 megahertz or even 32 or 36. But as more logic we packed in here, the more the timing dropped, obviously. So then 2 cycles later, so you see a 3 and then 5. So 2 clock cycles later at the 6th pixel, this is addressed by 0, so 0 bit and so on. So this is, the 3 is the 4th, this 5th is the 6th. So 2 clock cycles later, we have a valid output from the memory. So we disable the memory enable, and we use this address, this VRAM data is the output of the memory. We use this address for the font addressing. Again, for example, we display an R on the screen, so we need to load the actual character set. You see how complex it is, right? You would think this text mode is easy, but actually it is much more involved than direct frame buffer output. Also, no, I scrolled here. So then we disable the memory enable and enable the font part of the memory, the font, the second bank of VRAM where the font lives in. Enable this, read enable, and load it with the address of the VRAM. The VRAM, again, this is like R or something. So this is multiplied by 16 for 16 bytes per 16 pixels, high as in 8 bits, so 16 bytes for each character, just similar to a VGA text mode memory. And so we output this address, and again, this needs 2 clock cycles to have a valid address there on the memory output. This is then here 7th, aka the 8th pixel here. So at the last of this, so this is a previous pixel, right? So this is always 1 pixel ahead. And then we disable the font, read enable again, and copy this data, like assign it to the flip-flops. And this is without delay, because this is FPGA regular logic cells, not memory. And this is running with full speed, so no 2 clock delay stuff, but instantly non-blocking, available at the end of this clock cycle. So for the next pixel clock where we will draw this character then, so we will buffer this in row and attribute for the color. And again, this is attached to wires of combinatorial logic, so it's instantly updating here those colors that are here somewhere assigned to the foreground color here. So this attributes that we assign there instantly connected to those wires. So when we mostly actually for convenience to have this easier readable, also we could just open code it, type it there, but certainly it's nicer to write foreground color here in the code. So let's see. So then if it's not within those pixel preloading, then for each pixel we determine here the mask. Probably this so this is probably one of those things that is slowing the validated clock down, because this is now using blocking assignments to assign the color. So either if this bit is set for part of the pixel, either the foreground or the background color, probably we can most likely make this combinatorial logic. Maybe this would improve timing. Maybe even free some logic elements. This is a time of maybe optimization. In non-text mode, aka graphic mode, this is actually similar. Just that the preloading is actually simpler, because we have only one preloading of the bit mask every 16 pixels, because we have a 16-bit memory bus there. So we have, with each load, we have 16 bits loaded. So why do I have here? All right, and also this is only a little bit complicated due to double scan lining. So similar to VGA hardware, we are duplicating our lines. So this is, we need to reset our linear frame buffer position, and we need to reset this before the first pixel, because again, with the memory load delay, before the first pixel, we need to have this address. So this address needs to start in a negative offset before the first pixel with 0. And this is why I preload this at -16,1 and reset this. And then each line also, we output each line 2 times. So each, as you see here, each odd line, like first bit set in the Y position, we subtract 320 from our position to start again from the same scan line, effectively double scanning it for doubling the resolution for this graphic mode, as we don't have enough memory otherwise. So we have, the graphic mode is 320 by 240, while our full resolution is 640 by 480. And otherwise, so if it's not the special conditions of initializing or double scanning, then increment the clock here. Theoretically, yeah, could also be actually, and also complicated. Here's another trick. So we only increment this every second pixel. So we also double scan each X position. This is why this is incrementing by the first bit set of the X position, double scanning every second pixel as well. You see quite some tricks necessary for such simple stuff as doubling or halving the resolution of double scanning. Quite some tricks involved just for that. And then graphic mode preloading every 16 pixel here. So at 13, again, similar to the text stuff, so 2 pixels in advance, loads this here of VRAM address, assigning this here. And wait a second, why do we have this? Is actually a typo. We can, well, you see, it doesn't really matter much, but just to be nice, we can disable the, oh, wait a second, oh no, this is not a typo so much. This live on YouTube. This is actually whether to load it from VRAM or from text memory. We have 2 memory banks, 8K and 4K. So this is actually correct. This is once loading from VRAM and once loading from the font memory address. And then 2 clock cycles later, you see as 13 versus 15. We copy this to the red data, disable the memory read enable again, and copy this from the VRAM data bus to the pixel data. And then if it's for each pixel from this registered shadow copy there of our currently drawn pixel stuff, then output this again. Again, most likely this could maybe slightly be optimized with combinatorial logic. They're hardwiring this to shifting this non-sequential there maybe, but whatever. Then here's a color conversion. So this is again assigned for instant update. Again, most likely killing our timing. As I said previously, this was validating good for 26 megahertz. Now we are down to just some 16 or 15.8 something. So most likely all this all this blocking assignments most likely kill our timing here quite a bit. Maybe this could be optimized also another day or something. And then we assign here the color. We map the color from frame buffer RGB to the palettes. And so based on the color we are getting here from either the graphic or text. So we are reusing the same logic from the output of generating the bit stream of color data from either graphic or text mode, mapping this to the palette color, and then overlaying the cursor. So this is if cursor position here. And I applied a neat trick because we implemented in previous videos quite some hardware cursor stuff for Cyrus Logic, for S3 Verge, for Voodoo and Verge. Voodoo, not Voodoo. Voodoo 1 and Voodoo 2 don't. So better than the Voodoo and Voodoo 2 because both of them, I think, probably, at least Voodoo 1 doesn't have a hardware cursor. Maybe Voodoo 2 also not. I actually used the hardware cursor setup from the rendition Verite of all cards. Most cards have the first pixel of the cursor address, and this causes the issue of positioning the cursor slightly, partially clipped at the top corner there of the screen. And this is an issue if you have an icon like maybe even, yeah, I mean not an arrow, which also even an arrow cursor might be covered the first pixel, but like this kind of text cursor or other hourglass busy waiting cursors, they might be half covered in the topmost, so in the topmost corner there, as you see. And for this, some hardware, not all, for some hardware can simply not do it. You would need for those hardware, not probably the previous videos of mine have an example for that, but for this hardware you would need to on the fly update the cursor icon, which is super annoying and flickery. And other hardware does have a second offset register, so you have some hotspot offset register for like, this is like 4 or 6 pixels offset, of course complicating all the matter. And in all the hardware so far, I probably have only seen using the bottom right. So this cursor position here is a bottom right, very rarely used. I think I've only seen this in the rendition Verite. When I was implementing this, was like, what were they thinking? And I realized, hey, this is super clever. With this, you can totally position the cursor fully off screen, or only like 1 pixel or 0 pixel visible there on the top corner there of the screen, and without any offset and hotspot and whatnot, and yet still moves the cursor all the way here to the very last bit. Super amazing. I wonder, but there you see, so many hardware vendors have done something, and only rendition Verite has it in my opinion, probably most clever way that I shamelessly copied here. The patent for that, certainly after 30 years, is probably in the meantime most likely expired, although it's probably only 20 years. But anyway, so cursor, so hard overlaying here, and then so either, if this is a cursor, if the cursor is visible, output here the cursor, either cursor palette 0, 1 or 0, and or if it's inverted, or like inverted as in highlight, or transparent, then output the frame buffer. If it's not the cursor, then obviously just assign the frame buffer address. You see just the hardware cursor. I mean, hardware cursor, super simple, just so much lines, but on the other hand, so many logic elements just used for the hardware cursor, especially a whopping 32 bits multiplied by 16 plus a palette, so quite some registered flip-flops there for just this. This is some test signal fully optimized away, and also this transition, so this is assigning the output. So with 1 clock delay, copying the video signal from the generated video timing to the output pins here with buffered assignments. So with the end, just at the end of this clock cycle, being updated together with all the generated pixel data. And this is a memory mapped I/O system interface. So we are mostly through with this super fast run here through our Verilog video core stuff. So this is a memory mapped I/O interface with our PicoSoC RISC-V. Also a little bit tricky. So this is a select whether we are chip selected as in our video part here. So if not, select then reset some buffered. This is our buffered read register that I needed to optimize the memory transfer here. It actually was super tricky. That took me like nearly an afternoon to get working stable, because yeah, double buffered and memory timing glitches stuff. So if not reset, so this is reset not, negated inverted signal of if not reset. Then if the default state, so the default state we are not ready, we have not read or write enable. If this is for writing into our memory, so by default we are not ready and we are not writing unless this code is assigning this again. So this is a super somewhat tricky of the code of writing. So this is accessing the VRAM from the RISC-V CPU. Here this is address on our system bus. This is also somewhat optimized. I was already running out of logic elements, so I had here comparing the address. This costed more logic elements, like 10 or 12, just for comparing here 24-bit address. It is much more efficient just to check for 1 bit. So this is if the high bit of our address is not set. This is either control registers of memory mode and cursor and palette stuff, or our VRAM saves this. Just this line saved me some 10 or so logic elements. Then the address, so we have 8K for VRAM, and after the 8K VRAM we have 4K for the font data and second banked graphic mode VRAM. This bit here, again, previously I was comparing here for 2000 hex for 8K. That again costed, I was running out of logic elements already, had to save a little bit. So just again only checking for 1 bit. This is exactly the bit overflowing after 8K. This address line. So if over 8K, then font memory, and otherwise it's the VRAM bank. Also because I'm running short of logic elements here and we still need to implement keyboard and mouse, I have only implemented reading. So reading is quite complex, reading the memory from the RISC-V here on this side of the system bus. So I already copy and pasted the reading. The reading is this part. So you can only read the VRAM, not the font RAM, because yeah, YOLO, right now not enough logic elements left. So writing is easy. So if write, then write enable, assign the address, and copy the data from the write data to the font write data, and then tell the RISC-V CPU, hey, we are ready, fine. Because this default assignments here are 0, for the next clock cycle, the signals toggle back to 0 if we are not selected and if we do not get a new write. So this is only for this clock cycle set positive in this registered flip-flop there, and then the next clock cycle of the RISC-V CPU, if we are not selected anymore for a new write, then this will be automatically 0 again. And this reading is super tricky because we don't have a true, I had to learn the hard way, the ICE40 is not having a true dual port memory, so we can only read or write. We can only read and write. We cannot, like one is a read and one is a write port. They are not like full duplex read and write ports. So this is what we constantly output a signal here to the HDMI output, the video output. Due to that, we need to multiplex our reading because we constantly read for the video signal. So this was quite tricky to implement and get stable, because this is also why I very trickily timed the reading there of half of the pixel values. If you remember the 5, so the 6 and the 8s, or the 4s. Actually, we can scroll back to that, which is here. So text mode. So this is, where is it even? So the 4th, the 6th and the 8th pixel, because during this pixel clock cycles, our read is active from the video output. We can only read in the other pixel slots where we are not where we have this buffered preloaded value and we are not accessing the VRAM for loading pixel data. Very carefully timed, very tricky to implement and get working. It was another afternoon well spent on this. And the way this works is that this code here, so I have to do optimize more. I'm not really sure if we can optimize more, most likely not. So as you see, the higher pixel, the bits of the pixel address are active in the video output. So we check here for 0. So we only start reading at pixel clock timing X position 0 of all 8 bits. So only here 0 bit start accessing this. So this means if the video output is active, the RISC-V CPU will delay quite some, well, it's not so many, it's only like 2, because this is, so it's 4 clock cycles, but it's double data rate. So this is only half regular clock for 4 pixel clock, 2 regular system clock. So potentially idling here, waiting 2 real clocks to have free access to the VRAM. Then set our VRAM enable, assign our VRAM address, and then we need again to wait 2 clock cycles, because this is running with a pixel clock double data rate. Wait 2 clock cycles. I tried this the hard way, trust me, if you do this earlier you get random garbage. So 2 clock cycles later we can copy this, and the issue is we are running asynchronous with the RISC-V is running with half the clock, and this is a pixel clock. I got quite some deadlocking conditions if this signal is not 100% in sync. So due to that, I actually buffer this here. So we copy this, we disable the VRAM read because we are done reading. And then I set this buffered. So we need this bit to signal our own internal bus logic, like, hey, we still have here something buffered for you. So we copy this to the Vga read data, which is our register to the system bus. And then we mark ourselves like, hey, we have here something buffered. We still need to output this. So else, if not anything of this access pattern and we have something buffered, then we assign this VGA ready of, hey, you know what, we are ready, which are actually, by the way, I could actually try, I'm not really sure if I tried. Now that I think about this, maybe to do try if this works, maybe this could potentially reduce the delay by half, or maybe a clock cycle of the RISC-V core, maybe to do test for stability. Again, so reading from the text memory would only copy this here to the text memory. I tried this already. Right now I have only like a couple of 10-20 logic elements left. Previously I had already like 101% used. I had to already optimize the heck out of this address bit decoding stuff. So most likely I will at this point of time not waste any logic elements, any logic cells for font reading, because yeah, whatever. Just don't do this, just output data to the frame buffer. The reason I have VRAM access is actually for scrolling. So this fancy scrolling here, so we can toggle. So my code has either scrolling or not scrolling, and I can toggle this with the press of S for scrolling. So for the scrolling, we obviously need to read the VRAM back, and we only need this mostly for text mode scrolling. So this is why reading the VRAM for copying the data up there for scrolling, certainly quite nice to have, which is why I implemented that. And then the rest here, the rest of the file is only the control register decoding. So we have here the very highest bit of the address range, like FFFF is text mode. So this, the first bit in the highest address space there is toggling between graphic and text mode. That looks like that. So this is just one from the RISC-V CPU, from the RISC-V CPU, writing one bit to this control register, copies here this one bit, assigns this to the text mode here. As you see, write data first bit, first bit, assigning this here to the text mode, and this makes the output instantly toggle at the next pixel clock cycle. It will instantly start to output this video graphic versus text mode here. As soon as we toggle, it's just like next pixel clock, it's like here, it's there. And so then we have mostly writing for hardware cursor, and so hardware cursor X and Y, as you see, super easy assignments here, reading and writing supported. Of course, wasting a little bit. Theoretically, we could, if we later for the PS2, by the way, fun fact, I will definitely not do USB, because we definitely have not enough logic elements left after this fancy graphic code. And maybe we even disable like comment out or something here, this read support, because this, of course, reading this register of X and Y position, not really necessary. Maybe we just don't implement this, saving us a couple of logic cells for much more important PS2 keyboard and mouse. And also right now I even have not implemented the palette, so we would need to, as you see, we have here hardware cursor, palette of foreground and background. Theoretically, we need to copy this code or something similar, maybe more optimized for updating the color output palette. So this again wastes a couple of way too many logic cells for just reading or writing or something of that sort. Theoretically, we probably want to do this. That was a super fast walkthrough of everything I learned and all the bits and pieces of this HDMI, VGA, HDMI, graphic, text mode, output. Pretty satisfied with this result, pretty amazing in my opinion here, super nice in my opinion. Not much to be desired, quite some tricks employed there to get this to work. And from the firmware perspective, just to summarize this is a VGM file here, just embedded as a output sound melody stuff. But otherwise, we have here just some VGA, VRAM, and font, and then VGA, and then we can just normally write to this. For example, here's this RX32. On each character scrolling stuff, we just overlay this there. As you may be able to see there. Of course, right now the graphic mode a little bit, we can also reset this for. So also fancy scrolling. And fun stuff, hardware cursor. And otherwise, the only thing that we could probably do better, and maybe do not even really cost too many more logic elements, is right now the setup is a little bit funny that we have a 32-bit address space, but our VRAM is only 16-bit wide. And so we can optimize the performance quite a lot and even make programming a little bit nicer, because right now it's a little bit strange that this is a little bit non-standard of having here 32-bit addresses, but right now we are throwing away half of them. So only every 16 bits is a valid address to read and write for simplicity. And not only is it a little bit strange to program, it's not like that strange. It's not, you don't even notice it that much, because as you see, you can just assign this here of a 32-bit variable, just like the higher 16-bit are just thrown away to def null and data nirvana. Not anything done with that. But it's looking quite okay. Only if you look into the implementation details, you notice, wait a second, is it not 32-bit? And what is happening with the 16-bit gap in between? It's like, yeah, nothing. It's like, yeah. But we could actually optimize the read and write performance also. So this, because then with that we could make this, right now it's preloading 16 pixels or one text character and attribute. So if we make this VRAM for that, so this would make changing this to assign always 32-bit and making the VRAM here 32-bit. This should not really cost any extra logic elements, I would hope at least, because it's just distributing this. The only logic elements it costs is a buffer of buffering the data here. So yeah, it costs a couple of logic elements, but it would vastly double the performance. So right now writing to the frame buffer is quite okay. However, the RISC-V CPU is potentially writing 32 bits, which half are wasted. So even the write performance, if you wanted to, we could double the write performance, and we could, because we can only half of the time access for reading. So reading is relatively slow. Here for scrolling pixels, this is relatively slow. And so the write performance could be doubled with a 32-bit memory bus. Of course, this requires changing here all the logic again, touching this is probably an hour or 2 hours of work on changing this, because all the bits and pieces need to be changed for reading 32 bits instead of 16 bits at a time, and having here all the address computation a little bit changed, like 1 bit or something. Not much, but you need to do it and you need to test it, and usually it doesn't work and outputs some garbage, and then you need to guru meditate and think about it. But yeah, that would certainly be nice. It would make the RISC-V interface, the software side of assembler and C a little bit nicer, not like much, but a little bit. And certainly it would double the write performance, and it would actually nearly probably 3 times increase the read performance, because right now we have 8 double buffered clock cycles, and only from half of this 8 clock cycles we can access for reading the memory. And if we change this, we could, instead of 4 of 8 double buffered pixel clock cycles, we could probably, so with 4 clock cycles we read 16 instead of 8, so that would probably should mean that we can 3 times, not like double, but even 3 times higher read performance, because we should have 12 out of 16 clock cycles where we can actually read data. So that would certainly be much more amazing. But there you see, not only software but even hardware, there's always one more thing to, of course we can make it much more amazing, even with higher graphic mode and sprites, if we just would have more VRAM and logic cells, but that's probably something for a larger FPGA then. Next, because this is right now quite perfect, I probably leave it as it is, because, leave in the comments below how much you like this graphic core here of this amazing, probably hopeful anyway, stuff. This is, by the way, text scrolling there, obviously printing text on the graphic here, switching this instantly. Leave in the comments below how much you like this Verilog design series and the achievements we have done, and I hope you learned something from all the tricks. Even I, as a mostly, well, I always actually, maybe I grew up being more a hardware guy and then made software for 20 years. Actually, for me, this was really fun to do, which also why I spent so much more time than I probably actually should have done with it. But for me, it was super fun. I hope for you too. I learned really a lot, and I hope you too. And maybe I enjoyed it more than you watching it, but I hope you enjoyed it too. And with all the double data rate and double clocked, and certainly there you also see why is hardware sometimes glitchy, like if the stuff isn't synchronized of multiplexing address buses and buffers and read buffers, write buffers and stuff like that. And even after 20 years doing software with a quiet driver, hardware focused reverse engineering, over 500 supported scanners in our exact scan, but also doing PCI drivers, USB drivers, other embedded stuff, doing this intensively and working with such kind of constrained design, because one thing is for sure, it is much easier to work with a large hardware, like here hundreds of megabytes, even like here on the Ryzen, 64 gigabytes, like I certainly can make use of all of that. It's certainly much more challenging to make the best out of 5280 or whatever that were, 5280 logic cells, 120 kbit dual port block memory and 1 mbit single port memory. And next, certainly we do more software, because sound is amazing, graphic is, well, sort of, well, kind of, for the hardware, certainly kind of sort of amazing. And next, some more software, ping pong, Tetris and whatnot. We will have some fun eventually with that, and then also continue with more SGI, PS3 stuff. But I hope, even if you're interested in PS3 or Ryzen, Intel, peak bugs of cache out and Spectral Meltdown, also for us better to understand how do this Intel hardware vulnerabilities work. Also for you probably to learn those videos. I was also thinking maybe this IT show stuff here on the other channel, maybe in the future I rather, instead of 1 hour video of 8 topics or 12 topics, I rather maybe make one video with 1 or 2 topics, and maybe even go like I have sometimes done already in the earlier IT and security news updates, and like go through the paper of Intel cache out and explain how this line buffer cache stuff is leaking data slowly, 1 bit at a time. But certainly I hope it's helpful to give this kind of really low-level hardware perspective for you to learn something for reverse engineering PS4, PS5, PS3, SGA, MIPS stuff, and other NVIDIA Novo and other drivers and RGB lighting and whatever you want to work and reverse engineer at. And hope you learn something and inspire you to maybe get into this field or do something else. Maybe even a new business, of an idea of whatever you want to sell or something of that sort. Anyway, that's it for this in-depth walkthrough video of this video core. I'm pretty satisfied with the result, and hope again, as usual, leave in the comments below. I wish, of course, we could have had more fancy graphic. Again, of course, we can, if we sacrifice system memory, which I don't really want, because I rather have this memory for more fancy game logic and stuff. But if this is also the fun of reconfigurable hardware, if you want this more fancy, just half the system memory or buy a larger FPGA and synthesize this with more features and hack this up for whatever you want to use. That's it for today. I hope you learned something, and I hope you share and like and subscribe for all the next videos and fun stuff to come.